What if you could make any amount of money with the fewest coins possible, no matter how weird the denominations? CoinChange is a Pattern Mastery 100 legend and a favorite at Apple, Facebook, Microsoft, Salesforce, and Amazon interviews. This dynamic programming classic tests not just your DP chops, but your ability to break a tough problem into smaller, reusable subproblems. Let's crack the pattern that unlocks hundreds of interview questions. Let's break it down. You're given a set of coin denominations and an amount. Return the minimum number of coins needed to make that amount. If you can't make it, return -1. You can use as many coins of each denomination as you want. Now let's assess our approach. Brute force would try all combinations, exponential time. Instead, this is a perfect fit for dynamic programming. For every amount from 1 to the target, we'll keep track of the minimum coins needed. At each step, we look back at the best answer for current amount, each coin. This bottom-up DP builds the answer efficiently, and we only need a simple array. Here's the plan. Create a DP array of size, filled with amount +1, a value bigger than possible. Set DP0 equals 0, 0 coins to make amount 0. For each amount from 1 to the target. For each coin, if coin less than or equal to current amount. DP amount equals min DP amount coin, +1. If DP amount is still amount +1, return -1, else, return DP amount. Let's try to implement it using solution 1. Here we define a function called CoinChange. It takes coins, an array of coin values, and amount, the total we want to make. Our goal is to find the fewest coins needed to reach exactly that amount. We create an array called DP with size amount +1, so it has slots from 0 up to amount. We fill everything with infinity to mean, we don't know how to make this amount yet. It's like putting a giant impossible label on every box initially. This sets the base case. It takes 0 coins to make amount 0. That one is always possible, so we lock it in. Now we loop through every target amount A from 1 up to amount. We're building answers in increasing order. That's why it's called bottom-up dynamic programming. Inside that, we loop through every coin type. So for each amount A, we try every coin to see if it helps us build a better solution. Time complexity note. This double loop is what gives us O amount C, where C is the number of coin types. We grab the current coin value and store it in C to make the next lines easier to read. This is a safety check with 2 parts. First, A, C greater than equals 0 means the coin isn't too big. We can't use a 5-value coin to build amount 3. Second, DPA, C, equals infinity means the smaller amount A, C is actually reachable. Because if we can't make a C, then adding 1 coin C won't magically make a possible. This is the upgrade step. DPA, C, +1 means, if I can make a C using some number of coins, then I can make a by adding 1 more coin C. Then math.min DPA compares the current best known answer for with this new option, and keeps the smaller one. So we're always chasing the fewest coins. This closes the if block, meaning we only update DPA when the coin choice is valid and the smaller amount is reachable. This closes the inner loop. We've tried every coin for the current amount A. This closes the outer loop. Now we've built up solutions for every amount from 1 to amount. Now we return the final answer. If DP amount is still infinity, that means we never found a way to make the target amount, so we return -1. Otherwise, we return DP amount, which is the minimum number of coins needed. And that's how this algorithm works. It first sets up a DP array marking all amounts as unreachable except 0. Then it builds upward from 1 to the target amount, trying each coin and updating the best minimum coin count whenever a valid smaller solution exists. Efficient, simple, and elegant. Let's test our function using this input. Coins equals 1, 2, 5, and amount equals 11. This array represents the coin denominations we're allowed to use, and the amount is the total value we want to make, using the fewest number of coins. Here's why the solution works. We use a DP array where DPA stores the minimum coins needed to make amount A. We start with DP0 equals 0, because it takes 0 coins to make 0. Then for every amount from 1 up to 11, we try each coin and see if it can improve the best answer. For this test, when we reach 11, the best combination is 5 + 5 + 1. That uses 3 coins, and it's hard to beat because 2 coins would max out at 5 + 5 = 10, which isn't enough. And that's exactly what our program outputs, 3. The code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully finds the minimum number of coins needed to make 11 from 1, 2, 5, efficient and accurate. Now let's try another implement approach using solution 2. Here we define a function called coinChange. It takes coins, the coin values you're allowed to use, and amount, the total we want to make. The goal is to return the fewest number of coins needed to reach that amount. If it's impossible, we return -1. Time complexity, O amount C, where C is the number of coin types, because we solve each remaining amount once, and each time we try every coin. We create a memo map to remember results we've already computed. This is the memoization part. It prevents repeating the same work again and again. Now we define a helper function called DFS, short for depth first search. It takes rem, meaning remaining amount. So DFS rem means, what's the minimum number of coins needed to make exactly rem? If the remaining amount is exactly 0, we're done. We don't need any more coins. So we return 0. If rem goes below 0, that means we overshot, we used too much value. That path is invalid. We return infinity as a clear signal. This option doesn't work. Before doing any heavy work, we check the memo. If we've already solved DFS rem before, we instantly return the stored answer. This is what keeps the algorithm efficient. We set best to infinity at the start. This variable will store the smallest number of coins we've found so far for this rem. Now we try every coin option. Think of it like, what if I choose this coin next? We'll test all possibilities and keep the best one. We pick coins I, and subtract it from the remaining amount. So we're asking, if I use this coin now, what's the minimum number of coins needed to finish the rest? That result comes back as R. If R is an infinity, it means that choice worked. We add 1 because we used 1 coin right now, so the total becomes R plus 1. Then we update best to keep the smallest number of coins seen so far. Basically, take the cheapest valid option. This closes the loop over all coin types. At this point, best is either a real minimum coin count, or it's still infinity if nothing worked. Now we save the result for this rem in our memo map. So if we ever reach the same remaining amount again, we can reuse the answer instantly. We return best, the minimum coins needed for this remaining amount, or infinity if it's impossible. Now we actually start the recursion by asking, what's the minimum coins needed to make the full amount? We store that in ans. Finally, we decide what to return. If ans is infinity, it means no combination worked, so we return -1. Otherwise, we return ens, the minimum number of coins. And that's how this algorithm works. It first sets up a memo to remember solved remaining amounts, then recursively tries subtracting each coin and picks the smallest valid result while caching answers to avoid repeat work. Efficient, simple, and elegant. Let's test our function using this input. Coins equals 2, and amount equals 3. These numbers represent the coin denominations we're allowed to use, only a 2 coin, and the total amount we're trying to make is 3. Here's why the solution works. We use a DFS search to try subtracting each coin from the remaining amount, and we memoize results so we don't repeat work. If the remaining amount hits 0, we found a valid way, so we return 0 coins needed from here. If it goes negative, that path is impossible, so we return infinity. For this test, start with rem equals 3. The only option is subtract coin 2, so we go to rem equals 1. From rem equals 1, subtracting 2 takes us to rem equals -1, which is invalid. So every path fails, meaning there's no combination of 2's that can add up to 3. And that's exactly what our program outputs, -1. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully detects when an amount cannot be formed from the given coins and returns -1, efficient, accurate, and reliable. Let's wrap up with a quick recap of the coinChange problem, one of the most classic examples of dynamic programming in action. Breakdown recap. We began by understanding the task. Given different coin denominations and a target amount, we needed to find the fewest coins required to reach that amount, or decide it's impossible if no combination works. Assess recap. We compared potential strategies and realized that brute force recursion would try every combination, quickly becoming inefficient. Instead, we chose a bottom-up dynamic programming approach, where we build up solutions for smaller amounts and use them to solve larger ones efficiently. Structure recap. We structured our logic around a DP array, where each index represents the minimum number of coins needed for that specific amount. By iterating through all coin values and all subamounts, we continuously updated the array with the smallest count possible. Implement recap. After setting up the DP logic in LeetCode, our implementation ran smoothly, efficient, clean, and easy to follow. Check recap. We tested it using multiple inputs on LeetCode, confirming that the solution handled all cases correctly, including the ones where no valid combination exists. The key takeaway here is that dynamic programming shines when problems can be broken into overlapping subproblems. By building up from smaller results, we turn a seemingly complex challenge into a simple, systematic solution.